I don't find my mouse.
Oh, the mouse doesn't show up?
No. Yeah. Okay.
All right. Okay, welcome everyone. It's my pleasure today to introduce Janusz Bonca from Ljubljana, who's visiting us for this week. It's a great pleasure to have him here. I mean, I've known Janusz for a long time now. He's a great friend, and I really enjoyed discussing physics with him. I visited Slovenia several times, but this is the first time that he's actually here in Boston. So today Janusz has worked on a great deal of problems, particularly focusing on strongly correlated electron problems, and lately with phonons. And today he's going to tell us about his latest research.
Okay, so thank you. Yeah, it's really great pleasure to be here. Of course, I like to travel, but especially I think it's very nice to visit such a great place that you guys here have, and great collaborators that you have. But just before I really get to the main topic, maybe I should just warm you up, and myself too. So just, for those few that haven't visited Slovenia yet, that I just prepared some pictures, for example. Just to see where I'm coming from. So now why this does not work? Oh, why does this not work? Somehow doesn't work. Maybe. Look at that. Okay, now it works. Okay, so just to place ourselves, this is Italy, this is Austria, here is Hungary, Croatia, and all this, and down that used to be Yugoslavia before. So the most beautiful sea is actually down the Dalmatian coast. It's really worth seeing. We have a little bit of sea, not much, but okay, it's just enough to wet your feet, more or less. But then this is our only lake, only island that we have. This one ended up on the lake. It's not in the sea. There's also a church. That's actually all it is on the island. It's just the church, but that's okay. We have castles, of course, since this is Europe. You cannot avoid castles and churches also. Our kind of probably most pictorial coastal town, Piran. This is Ljubljana, our kind of capital. There is a river, of course, otherwise, boring. But we also have, let's see if this works. Okay. This goes too fast. We also have mountains, which we are quite proud, even though we haven't done anything for them. They just showed up. But, they look fine. You can use them up too. Then this is our university building. This is here. There is no science being done. It's just administration. So sorry about that, but it's beautiful. In the old times, Tito, our kind of president, some people call him a dictator. Let's say he was giving speeches from this balcony. Obviously, it's a great place. Now nobody gives speeches here anymore. It's just Zoom or something. More mountains. Quite steep. As we heard, we also organize conferences. So this is one of them on Krvavec. It's a non-equilibrium conference. That's why it should be on the slope. So it's kind of, you feel non-equilibrium all the time. And so there are some few pictures. This is from just December last year. It was really nice, cold. You can almost see on the picture, it's quite cold, in fact. So rather good scenery, I would say. I'm trying to kind of, show you my artistic side here, which this is all it is. It's kind of going to end up pretty fast. Okay, so now we go back to the subject. Sorry about that. So the main motivation here is are actually these pump probe experiments. The experiments that are trying to kind of send the system from equilibrium to some non-equilibrium state. And then especially kind of fashionable is you try to get some non-equilibrium metastable or longer stable states. And so the question is, can one use laser to change interaction between electrons? This would be kind of quite interesting if one could do that. So that you could, if you could increase interaction between electrons, you can actually go from one state to the other. Like, for example, you could go from some kind of mod charge density or some charge density wave to like a conductor or something like that, or maybe even induce superconductivity, which kind of is still being under question. So here I'm going to talk about very simple model. But this simple model turns out it really gives you what one is looking for, which is I'm going to show you that you can just by laser pump you can switch between interactive or repulsive interaction between one pair of electrons that are actually subject to phonon degrees of freedom. So, of course, the physical realization of this model could be still quite under question, but at least there is some, I mean, the calculation that I'm going to show, it's actually quite accurate, it turns out, in terms of numerics. So there is no approximations. One can actually check whether with increasing the Hilbert space, one can get the same results, and that's what also turns out to be the case. So it's a pure quantum mechanical calculation, which is quite exact, because of course the system is simple. You know, it's not very complicated system. So it's not that because I'm so smart. It's just because its system is simple. So anyway, but it works. Okay, so. Yeah, well, we have collaborators, that's fine. Oh, shoot, I thought that I should not skip this slide. So that's Marcin Bierzejewski. He's an extremely smart guy from Poland. We are very good friends. He's mostly working on correlated systems lately on many body localization problems. So sometimes I work as his student and sometimes he works as my supervisor. Actually, these are not quite the same, but yeah. Then Denis Golish, he made a PhD with me, and now he's becoming extremely independent and working with other methods that he actually devised and learned in Switzerland and then later in the States. It's mostly on the level of DMFT methods. Then this younger guy, Clement, he's actually currently my student. Also very smart guy. So yeah, okay, I was already kind of mentioning this experimental motivation somewhat. So of course there is this famous problem that is this hidden state where Dragan Mihailovic, who is essentially in the same corridor as I am, kind of found out, of course, with his collaborators. This is this tantalum disulfide problem, which is still, of course, the results, the experimental results are totally solid. So you can go from insulator to metal, which is very stable. It's a kind of a hidden state, but it's stable state. But the theory here behind is still not quite known. And of course, there are other attempts like this possible light-induced superconductivity. This is already kind of a, like a holy grail for many years, and it's still not quite clear whether this really works or not, but it would be great, of course. And then there have been also some related theoretical works where they were using the same or very similar, actually the same kind of model that I'm going to present. So let me just go to the model so that we don't kind of draw this too long. So the model is like a Holstein model. Those who know the Holstein model, you would recognize this, and you just kind of take this away here, and this is a Holstein model, very simple. So now we put this square here. Of course, the big question is how to justify this, the fact that now there is no linear term. Of course, we know that usually linear terms are the first terms that we have to take into account. So this is just coupling of the electron density now to the square of the displacement of the oscillator on the same side, right? So here the argument is that there are some cases, some models, or I mean some materials where this linear coupling is prohibited by symmetry. So the only next possible coupling of density is like quadratic coupling. So this is kind of the main difference between this model and then the Holstein model. But now you see, if you look at this term is always positive. And this is not quite the same as with the Holstein model because displacement can be plus or minus. So this is always plus. So therefore, this prefactor here, the sign of the prefactor is extremely important. If it's plus, it's minus, it's a big difference. And so this thing, since you see here it's the x squared, right? So x squared, imagine you have a spring constant, is k times x squared over half. So this obviously, this term will modify the spring constant in the presence of electron. That's the way to understand this term here. So, but anyway, then we drive the system. And the way we drive it, we drive with a uniform homogeneous field, electric field, like a dipole coupling, if you want, that actually just excites the whole set of phonons everywhere just through the displacements. So this is really dipolar like coupling. And so we send the pulse in. Pulse with the rather well-defined frequency omega drive, and then how well it is really defined depends on the sigma here, obviously, right? Smaller sigma, less defined, bigger sigma, or the other way, more defined, right? So, and the other thing that makes this model really simple is that we are only taking into account 2 electrons for now. There are smarter people that can do more electrons. They're also in the room, but I can only do for now 2 electrons. So single site. Imagine you have a single site. On the single site, you can have 0, 1, or 2 electrons, right? With 2 different spins. Now, as I said, if you take just the single site part of Hamiltonian here, you can, if you go back to the, to the momentum and the displacement representation, then you can very easily figure out that this term here just renormalizes the spring constant here, as you can see. So therefore, the frequency now depends on the density of electrons on the site, right? So now, in kind of a pictorial way, let's say you have four phonons, like your oscillator is in the 4th excited state or the 3rd excited state. So there is no electron, it's a 4 omega naught energy. There is 1 electron, it's reduced if G is negative. I just showed this for the negative G. If there are 2 electrons, it's even more reduced, right? So now, of course, this is not my idea. This was done by Kans and Millis, kind of this original kind of thinking, or maybe some people even before. So they said, okay, let's compute the binding energy. So the binding energy is the energy of 2 with 2 electrons plus energy with 0 electrons minus 2 times energy of 1 electron. And then let's see what's the sign of this binding energy. So if it's negative, then of course this state will have lower energy than, So it turns out that this binding energy, independent of coupling, it's always negative for any G. So positive or negative G is always negative, but it's like extremely asymmetric, as you can see. What is also kind of interesting, and it's not the same as one would have a Holstein model, is that more phonons you have on this side, providing you're comparing systems with exactly the same amount of phonons on the side, more negative is this binding energy. It just linearly depends on the number of phonons. So that's kind of this idea that now imagine that you're exciting the system, you put more and more phonons into the system, you're cooking it up with a laser pulse, for example. So you're producing more and more phonons, and then the idea is that the system would become more and more bound, because the binding energy, this, of course, very naive thinking now, the binding energy would increase with the number of phonons. Of course, this is not exactly what happens, but this was kind of this original idea, and we were trying to test this idea on this kind of quite realistic system with this kind of realistic approach. So this is kind of the only page that I will show how this our method works. This method I have kind of, it's actually quite old. Just thinking of this number, that means I'm also old because I'm on the same paper. It's kind of not so good. But okay, I guess I can survive for now. Start just with one electron. Let's say that the method was originally actually defined on the infinite lattice with one electron. So let's say, but now let's say that we have what? 6 sides. And so the first state is the state with no phonons, one electron here. And since we are taking into account translation invariance, this is the only state. All the others are translation invariant, so you don't need to think about them, right? I mean, computer just knows about this state, Bloch state, right? And then you add to this state, to this original state, you act on it with the kinetic energy and also the electron-phonon coupling energy. Just in this case, I just take like the Holstein model case, for example. So which means I just sum those two terms and I put them on some power, NH. So this power will actually tell me how many states I will kind of finally generate. So now in the first generation, what happens when the kinetic energy acts, this guy can jump left or right, but since those two states are identical in terms of translation symmetry, I have not generated any new states. The only state that I generate is when I act with this guy and then create a phonon here on this side. So in the second generation, I have only one new state, which is great. If it's going to go so slowly, it's perfect, right? But of course it doesn't. So then in the second generation, I create, let's say, 2 phonons on this side. But now when the electron jumps left or right, actually now I get 2 different states. So state with the phonon on the left from the electron and the phonon on the right from the electron. And now you can imagine how this thing goes on. So that's how the variational state is defined. And now it turns out that you can do this on infinite lattice, right? And then if you do this on the infinite lattice and you go to like 16 generation, you can get the energy of a polaron down to 16 significant digits for the thermodynamic limit. Big deal, right? Of course. But then it was, I mean, that time, this was a big deal because all these other approaches could only get 4 or 5 digits, which again, I mean, who cares? But okay. Yeah, now for 2 electrons is the same. Of course, you can start with 2 electrons on the same side, or you can actually do some linear combination where you put these 2 electrons in the beginning, and then you just crank up the system. So this is, you know, it's very simple, very simple. So what I will then compute is like a density correlation function. So this object will tell me, for example, what is the probability, actually, what's the probability to have electrons at a certain distance? And then if I sum this thing over all distances, I should get 1. So this is really like a probability, really, right? Then I will compute average distance between electrons. It's very simply defined. One could do it with a square and then the square root here, but doesn't matter. I mean, it does, but we just did it this way. And then compute different parts of the total Hamiltonian, like the kinetic energy, the coupling energy, and so on. So this is kind of, it's very dense picture, so you have to kind of catch your breath now. So what happens here? So here, what we do, we start with the ground state of the system. So we put a certain coupling, which is like this. You see, it's a very small number. And it turns out this number should not be too small, because if I would take here minus 0.2, then my parabola would go downwards and the system would be totally unstable. then I would need like the fourth order x to the 4 to stabilize the system. But I don't care. I just say, okay, I will just limit this thing to like omega naught over 8. Omega naught is 1, so the phonon frequency is just 1 always. And then I use a certain driving frequency. In this case, I just took this optimal driving frequency of the pulse. I think I should have a picture of the pulse somewhere. No, not here. This is this driving frequency right here, right? Omega naught is 1, and this one is in that case just a little bit below. There's a picture of the pulse that just disappeared. That's fine. Okay. So starting from the ground state. So the ground state, because there is a small little Coulomb repulsion in the system, just to push the electrons apart. I do that on purpose to see what the effect will be. I send in the pulse and then observe, for example, what happens to the average distance between the electrons. And then I do this for different amplitudes of the pulse. I'm trying to find some optimal amplitude. So I see that actually the average distance drops and then it maybe starts going up a little bit again. So it kind of looks good. And then what I do some time average over this regime where the pulse is already switched off. And this red line here is the time averaged G. So which means that now, before the electrons were apart, now they tend to be kind of bound. This is the total number of phonons generated during this pulse at different amplitudes, and also different parts of the energy, like the total energy, of course, it increases. So, it increases quite a lot. This is the coupling energy. This one is always negative for negative G. So it should go down, right, from 0. And that's the kinetic energy. It kind of increases a little bit. And so this is now the color plot of this function. So actually this hump, this thing is actually this stuff here at 0, times 0, right? And then the times goes on. Then you can see how these two electrons, they jump together. And here there is no more pulse. They actually remain together. So kind of looks pretty good. Then the idea was, so how about positive G, right? The positive G should also, in the atomic limit, also lead to binding. Well, it turns out it doesn't. So here we start with 0 U, so U is just 0. And then we switched on the pulse with the same frequency as before. And then it turns out that the average distance increases. So it starts here and then kind of increases. This you can also see here. Actually, this was kind of funny. This is the total energy. For all those that have ever done some kind of driven system, it's kind of weird because usually the total energy, if you drive the system, always increases, no matter what you do. And then when you stop driving the system, it remains constant because of the, hermeticity and the, So see here, there is no more pulse. The energy is constant, but here it actually dropped. So as if the pulse would actually take back the energy from the system, but that's not really the case. So what happens here is that this electric field is oscillating, is driving the displacements more than they would be driven if there would be no field. And that actually then by default increases the energy through this term. So if one grabs this displacement and just drives it with the field, then of course you will get bigger energy. And then when you switch off the field, then this energy drops down again. So it's not really that the energy went back into the, in some sense, yes, but you were just like by force, you were driving the displacement. And for the positive G, you get something which is kind of then bigger and then it comes down. But this just, actually, when I was looking at this talk to refresh my memory, this thing just kind of, I just realized that I was not even thinking about that before. So here is this pulse. I mean, just like the time scale is okay, but of course the amplitude you cannot compare because it's not the same units. Fortunately, otherwise I would have to deal about the units anyhow, which I don't want to. So this is actually a consequence of Dennis, one of the co-authors, who was kind of bugging me. Can one actually define some kind of effective potential that these electrons feel? So the idea is that for negative G, for example, so this term is the only term that can be responsible for attractive interaction, because without this term, nothing would happen, right? And so then what I did, I kind of devised such an operator here inside, and this operator. So this is actually kind of a projection of, for example, on this function or on this whole function that projects out all the states where electrons are the given distance j, right? So this V of j over t actually measures how much of this interaction is due to the states where the electrons are at a certain distance j, right? And then if I sum this over all j, I will obtain back the whole interaction part, right? So if I sum this over j, I get the whole interaction. So this is some kind of like effective potential. So then I plot this just the same way as before. This is time, and then this is this V of j of t. And so you see here there is almost nothing, because in the ground state there is almost no phonons. And then you start driving, then the phonons start to emerge because you excite them, right? And then at the end, these phonons end up kind of this zero means that these are all the states that are doubly occupied states. So all the phonons are actually more or less on top of the states that are doubly occupied. So it really, these phonons are kind of now they are should switch from Slovene language to English language. They're the glue, right? I mean, essentially, these phonons are the glue. That's why these guys like to be together, because then their energy, the phonon frequency is smaller, right? And then somehow seems to me that, I mean, it seems like it's very hard, when you go to systems that are away from equilibrium, you cannot think about what is the lowest energy, because you're already very high up in the energy. So what the system does there, maybe like maximum entropy, I don't know. I mean, it's kind of hard. But anyway, so then you see now the really cute thing is that if one changes the driving frequency from 0.9 to 1.1, just what is that? 20% change of the driving frequency, the picture is totally the opposite. So now suddenly this potential actually shows more like repulsion. So because this is negative, here it's negative, so the electrons would want to go apart, right? And so here these curves represent the time averages from here to here or from here to here. So this blue line is actually time average here. The red line is time average over here, and this is in the ground state. And I kind of like this. I thought to call this like a Klingon something, but those who like to you know what is Klingons. Yeah. So anyway, okay. So now this is getting a bit more complicated, because we have seen that just a slight change of frequency, of driving frequency, can make a big change on this effective induced interaction. So what we do here is we take, for example, we choose a certain driving frequency, let's say 0.9. We compute time evolution of this density correlation function, and then we time average like this. And then we plot this time average just here on a single line. And then we do this for different driving frequencies from 0.7 to 1.4. Each time we do the same kind of time average, and then we plot this. And so here now you can see very nicely how this is now time average G of J, right? So obviously here, in this regime, the situation is almost the same even after the pulse as it was in the ground state. It's not much, so it's like, turns out that the system did not absorb any energy. And this you can actually see from this correlation function here that actually measures how many phonons are actually absorbed by the states where, again, electrons are at a certain distance J. So if I sum over all those are sides here from -16 to +16, let's say if I would sum this function, I would get total number of phonons. And this is total number of phonons here. You know, it's actually quite large. It goes like to 10, you see. So here you see there is almost no absorption after the pulse. So you send the pulse in, and since the pulse is totally off resonant, nothing happens almost. And then you increase frequency, then you get into this regime where electrons actually get bound. And you see, if I compute averages this way, so this is now the driving frequency, you can see there is a quite obvious or very large dip at 0.9. This is the case that I'm showing all the time, right? But then you increase this driving frequency, then you get to back to 1, and then you get to the repulsion part, right? So here is repulsion, here is attraction, and this you can see very well from here, because if you go straight up, you can see that in this regime there is obviously a repulsion between electrons. And somehow you see these phonons, so these extra phonon excitations are kind of following the position, or like this, whether the electrons are together, then the phonons are also where the electrons are. And here also, when the electrons go apart, the phonons, these excessive phonons, are also following the electrons away. Yeah.
Giannis, can I ask you a question?
Mm-hmm.
So in the attraction repulsion figure, what's the dotted blue line around 6 or 7?
Right. So this, so these lines just represent time evolution at 0.9. This is time evolution here.
Oh, I was referring to the figure in between where we look at the average.
Here?
Yeah.
Yeah, this, okay, this dotted line represents kind of equilibrium. So what is the change due to against equilibrium value? In equilibrium, you would get this kind of average distance, or essentially almost no phonons. You don't even see it. This is not 0, but it's almost 0. So this dotted line represents equilibrium value before the pulse. This thing almost starts at this turquoise dashed line, but not completely. So again, this is, of course, you could ask, yeah, why did you use this kind of U 0.5? Well, just because I wanted to show, or we wanted to show that really you get attraction, right? That you have electrons that are further apart, and then they jump together. Now, if one uses U equals 0, then of course you already start with the state. Now, this could be debated whether these electrons are here really bound, or this is just because I have essentially like a system that has like a fixed boundaries in some sense, right? But definitely you see there is a huge difference between, you know, these density correlation functions or here when they kind of jump together again. So this is for U0. I mean, you see the same effect, but maybe this is even much more kind of spectacular, because you really have pushed them apart in the beginning. And also, the one thing you should remember that, you know, this G is very small number somehow. I mean, in some sense, you can compare G to this, right? Somehow in some non-dimensionless units, no? So this G can overcome this Coulomb repulsion here, kind of important. And then, so here, and here it's a nice comparison between negative G and the same value, but positive. So minus 0.12 plus 0.12. So now why is this important? Because many works before, also these theoretical works, kind of suggested that the sign of this interaction, this nonlinear quadratic interaction, doesn't make any difference, but it does. I mean, obviously it does. I mean, huge difference. For example, here you never see any kind of attraction. It's just repulsion. because somehow, see, this is the equilibrium and position, and then they go apart. And the same you see in this kind of absorbed phonon degrees of freedom. These two dots represent essentially single side binding energies for this parameter and this one for this parameter. Of course, you could now argue, yeah, why didn't you compute here? Well, my answer is, of course I did, but it doesn't change much. So it's still repulsive. Also, if I compute at this point, where the atomic kind of atomic limit binding energy would be kind of equal. And this is also maybe interesting for people that would like to do this with some kind of other methods, but for finite density. The question is, how is this stable? So in terms of the Hilbert space, in terms of how many phonons one allows in the calculation. So the method actually works in such a way that for these cases that I show here, the maximum amount of phonons is 16 in the system. This is the total amount of phonons in the system, and they can be kind of distributed anyway, right? They can be close to the electrons or further or something like this, but they're distributed somehow the way that this kind of naive construction of this variational function was shown before for a single particle, right? And then one could always have this kind of, it was nagging me whether maybe the special construction of the variational wave function, I mean, I'm saying variational, but this statement only makes sense if one does the ground state, right? Otherwise, variation doesn't mean anything. So if maybe my system was not kind of promoting this binding because of the special construction of a wave function, so then I decided to make a check, and I then constructed variation states, or like Hilbert space, where I only allowed maximum of 2 phonons per side, only anywhere. And so you can see that you still get the same physics. It's maybe not quite the same, but it still works. Now, what is especially interesting that, you know, if you look at the operator x squared, right? This x squared operator, when you put it in the second quantization, consists of a dagger, A, and AA, right? So this kind of 3 operators always change or don't change phonon number by 2. So it goes from 0 to 2, right? So essentially for the actual Hamiltonian, there are only 2 phonon states that are important here. Now, why then one would imagine, oh, just throw the states with 1 phonon away, because, you know, Hamiltonian always kind of, if you start from the ground state, it would always jump over the 1 phononic states. Or better to say, if I compute the ground state without any driving, my states are only 0 phonon or 2 phonon states, plus the electrons and so on, right? But then the trick is, you see, if you want to do the driving couples to the displacement. And it's a dipolar coupling. So you need displacement, which means you need also single phonon states for the driving. So somehow, if one could actually fool the system just to throw away these single phonon states and still do the driving, somehow it would be even better, because then you would only need 1 extra phonon excitation per side to actually show the same mechanism. So this detail may be only interesting if one is thinking to go to finite doping, where, of course, because of you would have more and more electrons, you would need much bigger Hilbert spaces, and then it's worthwhile knowing that this effect persists also for not to have, you don't need to have too many phonons and still have this effect. And yeah, so this is kind of for the end, kind of a little bit of a movie, you know, always try to be entertainment. So this, you see, this is time average, and this is also time average. These are driving frequencies, sides, essentially distances between the electrons. Of course, you can always say y minus 5 and plus 5. Well, we have actually two distinguishable particles, spin up and spin down. And so the spin down can be to the right or to the left of the electron. So that's why also, besides I kind of like symmetry. So, you know, sorry about that. Of course, the only useful information is only in half of such picture anyway, because it's totally symmetric. But anyway, so what you will see here is actually what happens really as the time goes by. But this is in a parallel system. So here you will see for each different driving frequency, there is like 50 different driving frequencies here. You will see how the system evolves, right? So now this situation that you see here is actually this situation here. Which will not change much with time, right? So this is almost like the ground state. And here there is no extra phonons. I mean, yeah, I mean, the ground state has very little amount of phonons, but you don't see them here because of the scale. And so now we put on the driving. And yeah, this thing will tell us what is the current amplitude of the pulse. So this amplitude will go up and then it will come down. So this is just the prefactor in front of the sign. Yeah, so now the pulse is starting. You see this is increasing, and then here slowly starts happening here. And you see here and here, now you can actually see the phonons here. The electrons are getting together slowly. The phonons here. And then what is kind of quite interesting, I would say, is that, see, now the pulse is switched off. I mean, just by, you know, the Gaussian thing just goes down. And so this is kind of scary looking thing. I mean, it's, yeah, I don't want to comment. Hope you don't have nightmares. So yeah, but that's physics in this case. Who cares? So anyway, but you see, there is still something going on, but more or less in time average kind of, so this time average is not so bad because now this is really without time averaging, right? So this time average is not like some big cheating of some huge oscillations, but this is how it is. Yeah. Then just, oh, yeah. So this idea actually came from Marcin. So that's why Marcin is also part of the branch, because he had this great idea. I mean, he's always full of great ideas. I'm extremely privileged to be able to be his friend and working with him. So he said, how about double pulse? Because, you know, you could really excite experimentalists with the double pulse and to show that you can switch this interaction on and off, right? Great stuff. Well, it actually works somehow. That's really weird. So here, you see, we start as before with the ground state, and then we send in the pulse at 0.9 driving frequency. And then, you know, the electrons come together. And then you wait a little bit, then 1.1 driving frequency, and they go apart. Beautiful. The only problem here is that the total energy increases all the time. So essentially, if you would want to repeat this, right, then you would kind of have to cool the system down. And then the question is, what would happen to these phonons? Because you need phonons to I mean, somehow these phonons, as they kind of represent a glue to keep the electrons together. Here they also represent anti-glue to put them to keep them apart, right? Yeah. Anyway, so what is this? Is like the average distance, for example. Here you see the average distance is a function of time. Here the two pulses were kind of centered, so you can see it goes down quite a lot, right? The average distance, and then it comes up again, but not quite to the same. I mean, here it seems like they're further apart than they were before, but when you look at the average distance, they're really not. Kind of funny, right? But anyway, so this is what it is. And then everybody will say, oh, well, yeah, now you're cheating, because it's kind of mentally easier to get them first together and then to put them apart, because each time you do that, you send more energy into the system. And somehow the naive expectation is that more you cook up the system, more disordered will the system remain or become, right? So the question is, can you do it the opposite way, like to put them apart first and then get them together? Well, that kind of works too, but not so well. So that's kind of the opposite way. So first you start, again, I start with the same U.5, and then this is the pulse that gets them even further apart. You can see here, not so much, but there is something at least. Of course, the system is also finite, so you cannot really push them all the way to the wall because they bounce back. So yeah. And then another pulse, which obviously gets them kind of together. So somehow it works. Not so nice as before.
What size systems are you doing this for?
So anyway, okay, so the electrons can go up to like 16 sites apart. The total system is translation invariant. So they can go like this, but they can go forever, anywhere you want. So the way this thing, also for a polaron, the way this wave function works, this infinite kind of like on the infinite lattice is that you have a particle and then there is a cloud of phonons around this particle. And now if the particle jumps left or right, you just translate it back. And the boundary conditions are in infinity. So essentially you can compute at any k vector. But this trick only works for like for one particle or maybe for two particles if they are bound. If they are not bound, then of course they cannot go further apart anymore. So there's the problem. So that's, yeah, so somehow it's like two electrons that are on some kind of a hard string. When you get 16 sides apart, they cannot go further anymore because of the Hilbert space. But it's easy just to kind of, you just increase this Hilbert space more and more and see how the results change, and they don't change all that much. I mean, they change here. I mean, this when there is repulsion, of course. When there is repulsion, if I would increase this Hilbert space, they would go further apart, of course, because there's the idea of repulsion. But when it's attraction, it doesn't change much. And so this is the last thing. I'm not sure how I'm doing with time, but I'm sure I'm going to be stopping very soon. So this, yeah, so it somehow it's a little bit, it seems like unphysical that, you see, there is another story to this problem. Namely, my Slovene language is coming back again. There is another part of this story which I still did not quite resolve. Namely, there are these ETH, eigenstate thermalization hypotheses. And so this actually means that, for example, if you have a correlated or actually interacting system that has like no integrals of motion, or at least it has only a few integrals of motion. And if you excite such a system, this system after some time will reach essentially thermal equilibrium. So like if you take like a Hubbard model and you send the pulse in, you increase energy, you wait until this thing kind of equilibrates, then you will still end up with a pure function. But if you would measure some thermodynamic properties of this function, you will end up there almost identical to the properties if you do the Gibbs ensemble with appropriate temperature. So that actually means this is ETH somehow, eigenstate thermalization hypothesis. And it turns out that Holstein model belongs to the same class. And the very simple reason is that it's not exactly solvable. That's kind of very naive looking, but more or less for all the systems that are not exactly solvable, not because we are not smart enough, but because they are really not solvable, right? Because they don't have infinite amounts of constant or like constant of motion, then this hypothesis should be valid. So then from this, then the question becomes, how come that your system, after you end up with the pulse, does not kind of spread around, and why don't these electrons go apart? I don't know. It should not be like this. Then you say, okay, so let's try to do this like in a better way, and then let's think what is the next thing. Of course, this is kind of going against my idea to to get this kind of interaction that would be long-lived. So if one puts a little bit of dispersion, bit of phonons, right? This is phonon dispersion here. So you have optical phonons that now don't have Einstein frequency omega naught anymore, but they have a dispersion, and with the width, which is given by 4 times this hopping here. So this is the width of this dispersion around omega naught. You can go plus minus 2t phonon, right? So now we have dispersive phonons, which means that if you make a single phonon excitation on one side, this excitation is not an eigenstate anymore, which is what without the electron, of course, but it's going to spread out. You're going to have like a wave packet or something. And so then, well, then when you start putting this dispersion, then you start seeing that this kind of binding, these 2 electrons are slowly starting to kind of fall apart, but still not so much as you know, one would be afraid somehow, right? So for example, here there is a comparison. This is just the case with dispersion, but here there is a comparison of this average distance as a function of time for no dispersion and with dispersion. So okay, so we can see that no dispersion, really this thing maybe it's going up, but it's hard to say. I mean, one would need to kind of keep computing, but of course all this, I mean, on small systems, at some point you need to stop computing, because somehow it has to do with something which is called the Heisenberg time. So the Heisenberg time is the smallest time. This is kind of, okay. So if you look at the whole spectrum and then you look at the average energy spacing in the spectrum, this is kind of the Heisenberg time. And so if one actually increases the system size, this energy difference is going towards 0, right? And then in some sense you can only compute up to 1 over Heisenberg time, your time, you know, propagation. Then of course you can do it more, but then you're wasting energy. So anyway, but still, I mean, here there is a fit on some kind of exponential, but this exponential actually has even a constant. So it seems like as if this thing actually, yeah, increases slowly, but then it increases to a constant. And this is a double occupancy. Here it's even more funny because with dispersion, with a little bit of dispersion, this double occupancy jumps even more, and then it kind of slowly comes down, also in like an exponential way in average. And again, it doesn't seem to be reaching equilibrium value. So these turquoise dashed lines are again equilibrium values. And then, so anyway, this is just as I have kind of promised. This is now the conclusions. And I usually don't like to read my transparency. This is meant for the public to read them if they want to, otherwise just ask me some questions. So thank you very much.
Thank you, Yanis. Time for questions.
Yeah. I want to ask, can you go back to one of the first slides and show how the G2 gets to normalize? I'm trying to understand how the resonance effect goes.
G2.
So like, it was at the very beginning when you showed your model, you were saying that
A single side, you mean?
side.
A single this. Yeah.
So you're normalizing.
So look, if you take just this is, you know, the oscillator.
Yeah.
So this is the same as this plus this without this guy, right?
Yeah.
Okay. So now, so if you stick the displacement, so if you replace this thing with the displacement and all this stuff here, then it turns out that this spring constant is now renormalized by this term here, right? But this term, there is an operator here, which now on a single side, this operator is just a constant and could be 0, 1, or 2. And so this is the thing. Also, the sign of this G2 is important, right? Plus or minus, and you can see that since this can be up to 2 for two electrons, so 8 times 8 G2 over omega naught should always be bigger than -1, right? Otherwise, this will be, right? Then you will get it all flat. Yeah, I don't know. Yeah.
So trying to put these in experimental terms. In this model, so I imagine I get a metal where I don't care in a certain range that I have a temperature for the electronic temperature doesn't change much the properties of the electronic degrees of freedom.
Mhm.
Then I transfer heat coherently to a certain degrees of phonon moments. And then my system opens a gap and becomes localized in the electronic degrees of freedom. Which, if I say, okay, take the metal and I heat it up, incoherently, that's not going to
Right,
happen.
right.
So it's the fact that I'm transferring heat coherently or energy.
Yeah.
What's producing this effect. And it has to be resonant, because if you move away from this resonant, then you show that you're basically just heating incoherent.
Right, or you're not just heating at all.
Right.
I
But
mean,
then you
if
show
you're
the
totally
energy.
off resonance.
Right, but the total
Yeah.
energy went up, right? In the
Yeah,
you
yeah,
show the two pulses.
Yeah, it did, yeah.
So where is this resonant effect coming from? Because it's the transfer, because you're coupling to the electronic fields.
Mhm, mhm.
So are we assuming that those electrons couple specifically with single phonon mode, and that's where quadratical, and that's where it's giving the energy to the lattice?
Okay, so is this the question how to justify the model, or if, let's say, we do have the model and now we try to understand what's going on?
Yeah, I'm just trying to.
The second thing.
Yeah.
Yeah. Well, okay. The answer, the real answer is I don't know.
I mean, I think
Right?
it's super interesting, right?
Yeah, I know. And we could talk. I have some other things that are kind of interesting, but not here, that could maybe explain this a little bit. I don't have the transparency here, but my gut feeling, right, which I cannot really explain, is that somehow when you shine the light with just the right frequency, then the question, okay, so let's say you have you have ground state, right? And then in this ground state, it consists of all possible states, where electrons are together, they have very small weight, and then the states where electrons are apart, and so on. So when you shine the light in, it turns out as if the light is mostly, if the frequency is correct, it's just about right, it's mostly then absorbed resonantly where when the frequency is below omega naught, in these states where the electrons are together, because that's the only resonance that they can find. Now, the thing is that this is not, you cannot say that electrons are like, there are two electrons on the side. No, there is some probability that you have 2 or 1 or 0. So in fact, when I really look at the at what is really the double occupancy, you see the double occupancy, this is really the double occupancy. Instead of being 2, it's actually 0.07. So now if I would stick this 0.07 into this equation there, this renormalization, right, and then do the appropriate, I would get this total omega of n, right, would be actually close to that resonance somehow. Yeah.
Really,
but what is really here the mechanism? This is just some feeling, right? But
there's actually some couple of papers where they've shown that you can actually drive a structural transition by coherently hitting the sun into a state that you cannot achieve in thermal equilibrium, because that state, when you grow your crystal, it's thermally not accessible. But then you can take the sample, shine light, transfer energy into the lattice, and go to the other structures.
Yeah. No, look, I understand, but
no, it shows that transferring energy coherently is very different than it.
Oh yeah, sure, yeah. The thing is that the works that I was kind of relying on, especially this paper by Millis, they just start with some kind of instead of really driving the system, they just start with some coherent superposition of phonons, and then they go on from there. But this picture, how this thing really depends on the frequency, is actually quite crucial somehow, right? You have to have the right frequency. It's not just enough to cook up phonons and something will happen, right? So this is very important. You need to have the right frequency. Then it really works. Of course, there, to be very frank, right? We are actually waiting for the referees to see what they say. Maybe they say this is garbage. Then we have a garbage bin. But if they will be excited, and maybe then we can keep on working in this direction. But at this point, we are not really going in this direction anymore because maybe it's a waste of time. I mean, we have to see. Especially this square coupling to the x square is kind of, it's maybe hard to justify, but there are definitely materials where these people claim that this should be kind of the case because of the symmetries.
Right.
So, the thing is that the way I started this calculation, I started driving the Holstein model, but with the Holstein model, you can see a little bit of this effect, but really not, it just does not work. It does not work somehow for the normal model. So you have to do this, you have to go, even if I add some linear coupling to this square, it will kind of destroy. I mean, there will be a lot of oscillations. It's not so nice. It's just not so good. Yeah, it's strange.
Yeah, questions? I've got a question. So here, if you look at this picture, the initial state, the ground state, is actually a bipolar, right? Because there is an equilibrium distance between the two electrons. They're not just spread all over space.
Well, because they
there's
cannot. Well, but okay, as I mentioned, if I would keep increasing the system, these two branches would keep going further, right? Because I only allow this much distance between them, right? So they're kind of locked into a certain.
So you're saying that this is a sort of artifact of the.
Yeah, this distance is not, how to say, this distance is not converged in terms of finite size, right? But this distance is, that's the funny thing somehow. So
right, because I was surprised that after, the two pulses.
Yeah.
They seem to go to the same equilibrium distance as the beginning, right?
Yeah,
so I'm like,
it
looks like all the energy is the excess energy is trapped in in the phonons, and the electrons just
but imagine that there is a hard wall, so this guy cannot go beyond this thing. And then the other thing is that the way the variational space is constructed in this regime where electrons are much further apart, there is also less phonons available because the way I kind of do the wave function. That's why I was playing then with this other case. So this distance is not converged, but the effect is converged. So I mean, I had some. Well, maybe I have some here, but I'm not sure if I have some stuff. If there are some questions now, but I don't have that really available. So to show the same thing, as I increase the system size, you will see that this part remains almost the same. This just kind of goes a little bit closer together. If I go to smaller system, but this part kind of remains there. Yeah. Yeah.
Right. No other questions. Let's thank the speaker one more time.
Thank you. Thank you very much. All right. I don't know.